So in a previous lesson, I had actually drawn out all of the orbitals in order to explain electron configurations. So I'm going to quickly do that, and then in this lesson, I'm going to make your life a lot easier by showing you how we can actually simplify that by drawing what are called orbital diagrams. For the first example problem, I'm asking about chlorine. So just as a quick review, the electron configuration for chlorine is 1s2, 2s2, 2p6, 3s2, and then 3p5. Okay? And this is what I had explained. This is what I had drawn out. All right, 1s is going to be spherical in shape. So first of all, I'm going to draw my nucleus. Okay? Those 2 electrons that are in the 1s orbital, there is a very high chance they're going to be within this 1s orbital, right? 2 electrons floating around. Not a guarantee they'll be in there, but there's a good chance. Okay? Then there are going to be 2 more electrons in the 2p orbital. They can be floating, and they can even go into the region where the 1s was, right? The 2p includes everything that's within this purple circle. Then for 2p, it gets a little bit messier. Remember, it looks like this. So there are 2 electrons that could be in this orbital. There are 2 more electrons that could be in this orbital, and 2 more that could be in this one that's supposed to be coming out of the page, but I'm not very great at drawing. Okay, so a total of 6 electrons. And remember, these are the regions where you're most likely going to find the electrons. Then I look at 3s, a bigger circle, sphere, sorry, not a circle, sphere. Okay, so this is going to be your 3s. Again, 2 electrons within this region, likely. Okay, and then 3p. Notice the s's, the s orbitals, simply get larger, going from 1s, 2s, 3s. Same thing with p. 2p has the same shape as 3p, except it's just smaller. So 3p is going to be even larger. And notice you can fit a total of 5 electrons for chlorine in this orbital. Now, if you can imagine me asking you every single time you wrote out an electron configuration to also draw this in order to see what's going on with the electrons, your brain would hurt a lot. Okay? So instead, we have an easier way of drawing your orbital diagrams, and here's how we do it. Notice for all s orbitals, for the s sublevel, you only have 1 orbital. You have 1 shape. It's a sphere. And so we represent that with just a box. Okay, so I'm going to space out my electron configuration quickly for chlorine. Give me 1 sec. All right, so because there's only 1 orbital in the s sublevel, I'm going to just represent that orbital with a box. And these electrons that are floating around, in order for them to be stable, the rule is there can be 2 electrons in every orbital, but they need to have opposite spins. So while one has a spin upwards, the other one will have a spin downwards. And notice this is a half arrow. If you want to draw a whole arrow, that's totally fine. Okay? For 2s, again, you only have 1 orbital, 1 large sphere. And you have 2 electrons in there, so it's going to be 1 up, 1 down. For 2p, remember there are 3 different orbitals, 3 different shapes along the x, the y, and the z axis. So I'm going to have 3 boxes to represent my 3 orbitals in the p sublevel. Okay? There's one more rule I have to explain, and that is this. When you're filling orbitals, you first fill orbitals, each orbital with 1 electron with a specific spin, and then you can go back and continue filling orbitals. So this is what it looks like. I can fit a total of 6 electrons in the 2p sublevel. So 1 electron, 2 electrons, 3 electrons, go back, 4 electrons, 5 electrons, 6 electrons. Okay? In 3s, in that sublevel, I have 1 orbital and 2 electrons. 1 up, 1 down. For 3p, remember p has 3 orbitals. 1, 2, 3. Okay, I'm going to go up, up, up. That's 3 electrons. Down, down. That's a total of 5. So this, if I ask for the orbital diagram, is what I'm asking for, not this. Because while this is manageable with chlorine, as soon as I get larger, like when I talk about iron in a second, it's going to get really messy. And you'd have to draw your d orbitals, which gets even crazier. All right, let's look at iron. All right, for iron, the electron configuration is the following. 1s2, okay, so let's draw out the orbital diagram. So 1s has one orbital with 2 electrons, one up, one down. 2s has one orbital, one up, one down. 2p has 3 orbitals, one up, one up, one up, one down, one down, one down. 3s has one orbital. Remember, s has one orbital. Here I'm going to create a quick cheat for you. The s sublevel has one orbital. P always has 3. And D always has 5. And while we will not be drawing them, if you notice 1, 3, 5, F therefore has 7. And remember, each orbital can fit a total of 2 electrons in them. Okay? For 3p, 3 orbitals, 1, 2, 3, 4, 5, 6. For S has 2, 1, 2 electrons in one orbital. And then for D, I've got to drop 5 orbitals. 1, 2, 3, 4, 5. So I'm going to fill it 1, 2, 3, 4, 5, 6. So much more manageable than the monstrosity that I created up above. That is your orbital diagram. Okay, let's look at one last one. All right, for vanadium. There's my electron configuration for vanadium. Okay. I'm going to draw my orbital diagrams. 1s has one orbital with 2 electrons. 2s has one orbital with 2 electrons. 2p has 3 orbitals. 1, 2, 3, 4, 5, 6 electrons. 3s has 2 electrons. 1, 2. 3p has 6. 1, 2, 3, 4, 5, 6. 4s has one orbital. 1, 2. And for the last one, a lot of students say, well, if I only have 3 electrons, do I have to draw 5 orbitals? And the answer is yes. And the reason why is these electrons, even though you're going to have empty orbitals, you need to show that they are still present because electrons can actually jump between orbitals. So this electron could technically jump into that orbital. So by not drawing it, you're not acknowledging that it exists. And you're making it seem like you're talking about the P sublevel and not the D sublevel. All right, so let's look at 2 more examples for drawing orbital diagrams. The first one, if you notice, is oxide, O2-. So what's different here is now I've either added or gotten rid of electrons in order to form an ion. And in this case, because it's O2-, I've added 2 electrons. So let's see how that's going to affect my, first of all, electron configuration and then my orbital diagram. So if I look at oxygen on the periodic table, its electron configuration is going to be 1s2, 2s2, 2p4. Now I have a 2- charge in this problem. And so what that tells me is that I'm going to add an additional 2 electrons to oxygen, okay? So while this originally, the electron configuration was 1s2, 2s2, 2p4, I'm going to add 2 electrons to it, making this 2p6, because you add and take away electrons from your highest energy level. So in this case, it would be 2p. All right, so that's the only thing that's different. When I have a 2- charge, I add electrons. When I have a negative charge, I add that many electrons to the electron configuration. When I have a positive charge, I take away that many electrons. Okay? And so for drawing the orbital diagram now, it's just going to be like before. I've got 1s2, so I've got 2 electrons, 1 up, 1 down, 2s2, and then now 2p6. So notice I have an octet here, which is the whole point of me adding those 2 electrons. So now oxygen has 8 valence electrons. It has a full outer principal energy level, and it is stable. Okay? Let's look at potassium ions. Let's look quickly at potassium itself. So not as an ion, potassium would have an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, and then 4s1. So let me write it down here. Now notice potassium has a +1 charge. So what that means, and remember it's +1 because I don't include a number behind it, it's implied to be a 1 for us. So I have 4s1, so I need to remove an electron from the highest energy level, which is 4s right there. Remember, the energy of your electrons increases as you move from left to right. So 4s is the highest energy. So I'm going to remove that 1 electron. Well, when I remove that 1 electron, I actually completely get rid of this orbital right here. So what I'm left with is 1s2, 2s2, 2p6, 3s2, 3p6. That is 8 valence electrons because the 3rd energy level is now my highest energy level, and I've got 8 electrons in there. So that is why potassium, when it forms an ion, will always have a +1 charge. Okay, I'm going to fill in the orbital diagrams. And notice my 3p sublevel is now full. It's full, and I don't have that 1 extra electron that potassium lost.